Culture.
Welcome to our comprehensive guide on implementing architectures from software architectural design. Today, we are tracing the evolution of software architecture, understanding its pivotal role, and diving deep into the art and sciences of bringing architectural designs to real life implementations. So, me, roll number 34, Shivam Nikam, roll number 35, Palash Panchal, and roll number 39, Abdaminav Poonawala are presenting to you implementing architectures from software designs. So, every architectural blueprint acts as our guiding star, but translating this guide into a tangible, functional, and identical system on the ground is where the real challenge lies. Throughout history, great constructions, be it the pyramids or the modern skyscrapers, depended on precise blueprints which were followed and executed to implement and bring about those buildings. Similarly, in the world of software, our architectural designs set the foundation for the robust, scalable, and maintainable systems. Coming to the mapping problem, implementation is the one phase of software engineering that is not optional. So, when we embark on the journey from architecture to code, the mapping problem often stands as a formidable challenge. Thinking of it as a translator bridging two languages, ensuring the essence remaining intact. Now, imagine a scenario where where a building's blueprint showed a room, but when constructor constructed the door, the hallway was missing. Such mismatches in the software can lead the system failures, security vulnerabilities, and performance issues. So architectural based developments provides an unique twist on this classical problem. It becomes in large measure a mapping activity. So each design decisions need to be perfectly mapped into into the artifacts of its implementation, and maintaining mapping means ensuring that our architectural intent is reflected in our constructed systems and it does not drift away from the main idea which was in the design decisions. Common element mapping. Architecture is replete with common elements, modules, interfaces, or components. These are our building blocks. But how do we manifest these components and connectors which we know, which are part of our software designs, into our code? So model becomes classes, interfaces turns into APIs, and components might be realized as microservices or libraries which we leverage in our software ecosystem. It's transformation that brings about the real solution and or that transforms our design into our implementation. So normal components and connectors, they can be used in our design processes, and then they can be shifted or translated into these modules or API functions through our implementation part. One way versus round trip mapping. One way versus round trip mapping, the dynamics between design and code, a pivotal question arises. Should the design always dictate code, or should the code occasionally influence the design adjustments? So this chance between the design and the code is captured in the concept of one-way versus the round-trip mapping. Architectures inevitably change after implementation begins for maintenance purpose, because of time pressure, or because of new informations. This constraints bring about the drift between the implementation and the proposed solution in the design process. Implementations can be a source of new information. We learn more about the feasibility of our design when we implement that. While implementing, we might think of how to optimize that. We might think of how this solution can be made more scalable than it is proposed in the design itself. So this is the mapping circle that we have to perform during our design decisions and the implemented artifacts. Architecture implementation frameworks. The ideal approach: developed architecture based on a known style. Select the technologies that provide the implementation support for each architectural element. So basically, as architects and as developers, we are not alone in this journey. So you need to set out and have a clairvoyant view ahead in times how our actual designs are going to be implemented. So the software community has blessed us with tools and methodologies, tailor-made frameworks to ease our voyages while embarking on the journey of making the designs into an implementations. So instead of going after a random design principle, we should go and select this tailor-made design styles, which can be easily translated into a particular implementations. So as we discussed earlier, the components can be converted into classes, the interfaces can converted into APIs, the connection similarly, this set patterns, maybe class diagram, maybe a particular use case diagram can be implemented in the design process itself. So the implementation is easier. Palash?
Economical example. Standard iOS STDIO framework in Unix and other operating systems, perhaps the most prevalent framework in use today. Style supported pipe and filter. Implementation technology supported concurrent processes oriented operating systems, generally non-concurrent languages like C. Here we can see that get burn rate from user, then to stream, then to compute the new values from stream to display the new values to the user. Let's delve into a tangible example. Picture designing a house. The blueprint outlines rooms, doors, and windows. But it's the bricks, mortar, and craftsmanship that transforms it into a livable space. Similarly, the Unix Studio framework is a canonical example in software illustrating how architecture intentions manifest into functional systems. Next, middleware and component models. This may all sound similar to various kinds of middleware component frameworks, Cobra, COM, DCOM, Java Beans, .NET, Java Message, Services, etc. They are closely related. Both provide developers with services not available in the underlying OS or language. Java Beans provides standardized packaging framework with new kinds of introspecting and binding. In the realm of software, middleware holds a special place. Analogous to plumbing or electrical wiring in a house, middleware might be out of sight, but the role is undeniable. Whether it's connecting databases or the unsung hero, ensuring the components collaborate seamlessly. Next, resolving mismatches. As with any translation, mismatches are inevitable. Something what's beautifully outlined on paper doesn't align with the reality of coding constraints, platform limitations, or performance consideration. Addressing these discrepancies proactively ensures our architectural integrity remains uncompromised. Next, hiding middleware and connectors. As systems grow in complexity, abstraction becomes our ally. Much, much morely about much morely about the aesthetics and safety, we can encapsulate middleware complexities with connectors. This abstraction not only simplifies the design but also ensures the modularity and maintainability. Building a new framework. While the software world offers a plethora of tools, sometimes our unique challenges demand custom solutions. Building a new framework isn't about reinventing the wheel, but crafting a tool tailored to our specific needs, ensuring our architectural vision isn't compromised.
New frame now we'll discuss new framework guidelines, right? So we've already discussed how you're supposed to build a new framework, but then when you go to build a new framework, what do you wander in the dark? No, right? There's certain guidelines that you need to follow, certain rules, certain patterns that have been established in the community that are easy to understand, easy to grasp, and easy to implement, right? Tried and proved patterns. So first you have to understand the target style. What type of architecture do you want? What type of end product do you want? Depends on the type of architecture that you're going to use, right? So you enumerate all the rules and constraints in concrete terms and then provide examples, design patterns, and corner cases. all right, and then limit the framework to the rules and constraints. All right, do not let a particular target's applications leak into the framework. All right, you're still just working on the framework. Right. So, even when forging new tools, right, it's crucial to adhere to established guidelines that ensure our custom frameworks are robust, scalable, and maintainable. And it's this blend of innovation and best practices that leads to software excellence. So now we come on concurrency, right? So what is concurrency? Concurrency in its most basic terms means running two things at once, right? Concurrently to each other. So, and in the current digital age, multitasking isn't just a human endeavor. Even software systems juggle multiple tasks simultaneously. Managing concurrency is akin to orchestrating a symphony, you could say, where every note, every instrument plays in harmony, delivering performance and reliability. Obviously, here the notes refer to programs, software, and code. And even if you look at our processors, we have multiple core processors that enable us to have the concurrency. So it's important to reflect that on our architectures as well, right? And it's also one of the most difficult concerns to address in implementation. So one of the ways you can do it is introduction of subtle bugs, right? Like deadlock, race conditions. And another topic on which the entire book's written. And it's often an architecture level concern where decisions can be made at an architectural level. And when done carefully, much concurrency management can be embedded into the architecture framework. Now we come on to generative technologies. All right. So now as we stand on the cusp of new technological era, new technologies are being established all the time. Automation emerges as our ally, right? Generative technologies, with their ability to auto-create parts of implementation, are revolutionizing how we approach software development, making our journey just smoother and more efficient. So, with sufficiently detailed architectural models, various implementation artifacts can be generated. So, entire system implementations, for example, skeletons or interfaces, compositions, all of this can now be generated with technologies that have been come up. Now, next we'll see how we need to maintain consistency. Now, we need principles, right? This also ties into the point where we followed about guidelines. So when we maintain consistency, right, one principle stands tall, which is having consistency across. So it's the bridge that ensures our architectural blueprints and our code work hand in hand. This harmony, this consistency is what transforms good software into great software. So the few ways we can do is implement strategies for maintaining one-way round trip mappings. So in that we can maintain and create traceability links. Uh, for example, explicit links in a database, in architectural models, in code comments, etc., can all help with consistency checking. We can make architectural model part of the implementation. So when the model changes, the implementation adapts automatically. May involve internal generation. Now, also generate some or all of the implementation. And now we come on to our last slide, which is basically saying thank you. Now, as we conclude, remember our architectural designs are more than just diagrams. They are the soul of our software. All right. So thank you for joining us on this hopefully enlightening voyage where we discussed everything from mapping, architecture, frameworks, component models, mismatches, uh, and concurrency, and everything that you need to transform a basic idea or architecture into real software. The problems as guidelines that you need to keep in mind when going through this. This has been Abdul Manaf, Shivam, and Palash. Thank you for listening to us. We hope you learned something today.